In science, we use experimentation and observations and measurements to reach conclusions. But how do we know that those measurements and conclusions that we've drawn from them are valid? Let's take a look at that. Again, you should be turned in your package to page 20. Let's say that we had a simple task. We wanted to determine the density of water. Okay, that's fairly easy enough. So density is mass over volume. So we get a balance, get some water, plunk some water in a graduated cylinder. Maybe the volume's 56.1 milliliters. We put that water on the balance, get a mass, take the mass divided by the volume. We come up with an answer. So we say, okay, the density of water is 1.01 grams per milliliter. Well, how confident are you in that answer? Okay, is that really the density of water? Why do you feel confident in that answer? Why don't you feel confident in that answer? Well, maybe another group did the same thing, but instead of using the graduated cylinder, they used the beaker instead. They find volume, find the mass, come up with an answer for density. Does it really matter which instrument we use? Is that going to have anything to do in the confidence and how we feel in it? So let's say we did have a couple groups doing that, whereas one group, we'll call that the beaker group. They correctly measured volume and mass of water and did the calculations correctly and came up with the answers that we see here. Whereas maybe another group used a cylinder and they correctly made measurements and came up with these answers. Well, now how confident do you feel in your answer? So that's what we want to discuss here. So certainly one thing that we want to look at if we want to think, all right, I've got my answer, how confident do I feel in this? Well, let's think about the instruments that they use. In this example, there's a definite difference here. Our beaker only measures, you can see there's only every 25 milliliters that marks on that, whereas the graduated cylinder has every 1 milliliter marked on that. So there's a lot more guessing involved with the beaker. So just by the nature of the instruments that I use, I would feel a lot less confident if I had used the beaker than if I had used the graduated cylinder. So when you're designing an experiment, if you're making a measurement that needs to be exact, you want to make sure that you've taken the time to choose the most precise, exact instrument because that's going to have a pretty good impact on your final answer. Another thing, a huge thing that we do in science a lot, is we try to see if the results are repeatable. Now, if you were doing this experiment in real life and trying to find the density of water, you wouldn't just want to do what we just did in our example here, just do it once, take one mass, take one volume, divide it, and say, here you go, here's my answer. You would want to do multiple trials. And there is no magic number for how many you should do, but certainly I would say the bare minimum is at least 3. And if you do it 3 times and you get pretty consistent results, then maybe that's pretty good. There's some experiments you would need to do 1,000 times. If I do it 3 times and my 3 times they're all over the place, then I might do more times. But the whole idea is that if I'm consistently getting the same answer over and over again, or very close to the same answer over and over again, then I feel a lot more confident about my answer. And when you do different trials, it's usually a good idea to vary something if you can. Say, for example, the sample size. In this experiment here with the density of water, it doesn't matter how much water we use, we should get the same answer for density. So maybe I'll do it once with 20 milliliters of water, calculate the density. Do it again with 30, calculate the density. Do it again with 50, calculate the density. And that just tries to account for any inaccuracies. Maybe my graduated cylinders mismarked a little bit at the 20 milliliters. So if I only did 23 times, I'm going to be off a little bit every time. But by doing 20 and 30 and 50, I'm just trying to account for any misgivings there. Also, whenever we make a reading, we might be a little bit off once or twice. And so the idea is if maybe I'm a little bit off this time and I'm a little bit above the next time, a little bit below the next time, if I average all of my trials, then I'm going to have a better answer than if I just did it once and said, here you go. So our experimental answer is always the average of your trials. Even though you might do 3, 4, 5 trials, you only have one experimental answer, which is the average of your trials. So a term that we want to make sure that we understand the specific meaning of it, if we talk about our results, is a term called precision. And this idea of consistency that we've been talking about really is precision, because precision refers to how close together your results are. In other words, when you do one trial, did you pretty much get the same thing in the next trial? And did you pretty much get the same thing there? That describes your precision. If you have a good consistency or a good repeatability, that means you have a good precision. Now, just because you have good precision doesn't mean your answer is correct, but it is a good sign. If I see an experiment where I'm all over the place and one time I'm getting a really high answer and then a lot lower next, then I don't put a lot of faith in that. But an experiment that has a good consistency, good repeatability, in other words, a good precision, at least I know the process is pretty sound and pretty solid. Still might be wrong. Maybe my instrument was just marked wrong and I read it every time consistently, but if it was marked wrong, then all the answers are going to be wrong because of that. So if I was looking at two different experiments here, experimenter A and experimenter B, and you ask me, well, who has better precision? Well, if you look at these, just take a minute, pause the video now and circle the one that you think has the better precision. Okay, it's probably pretty obvious that experiment A has a better precision because the answers are all closer together. Whereas experimenter B, we have a much broader range. And again, not that experiment A's results maybe are better, but if I had nothing else to go by, I'd probably say I like experimenter A's experiment just because of the fact that it is more precision. It means it's probably a better chance of being valid, but not necessarily. Now, one way that we have to put a number on the precision is by calculating what's called the average deviation. And so this measures the precision of the experiment. And so the way we do this is we find the experimental answer. Of course, that's the average of your trials. And then we figure out how far off each trial is from that average. And that is called the deviation. And then we simply average those numbers. And so the average of the deviations is the average deviation. It'll make more sense when I show you an example. So let's look at this example. So we've calculated the density of lithium. We've done 3 trials. There's our 3 results. Now, if I were to ask you what the experimental answer is, according to this person's results, what is the density of lithium? Well, they wouldn't give me 3 answers. They would take the average of these. So they would tell me that according to this data, the density of lithium is 0.573 grams per milliliter. That's our average. Now what we want to do is figure out what the deviation is for each trial. So in trial number 1, we simply subtract the average from the 6.02, and we get this 0.029. That's the deviation. Now an important thing here is we're interested in the absolute value. So even if your deviation were to come out negative, we're interested just in the absolute value of the deviation. So you notice in my second example here, technically, if I subtracted those 2 numbers, that gives me a negative answer, but I just have a positive result. Again, I'm just interested in the absolute value. How much did it deviate? Which way? I don't care. So the second was 0.069. That's the deviation for trial 2. And then trial 3, our deviation was 0.040. So again, this difference here is what we call the deviation. So all I need to do is average those numbers, and that gives me the average deviation. Okay, again, that is a measure of precision. Now, the lower the average deviation, the better the precision of my experiment is. So we want to shoot for close to 0 for this. So if we think about those examples that I just showed you about the water, we had the cylinder groups, we had the beaker groups, and we want to think, well, who do you think would have the higher precision? Now we have some certain guesses, but let's look at the data. So we want to go ahead and calculate those, and I'm going to have you actually pause the video now, and you have the data there. So go ahead and calculate. In fact, I'm going to move the slide again here, and on our next slide, here we go. I want you actually to pause the video now and calculate the average deviation. Do one for just the beaker people, get an answer for the average deviation for the beaker people, and then do another one for just the cylinder people, and come up with that there. So pause the video now, do that, and then restart it when you're ready. Okay, welcome back. Let's make sure you did this right. So first thing you should have done is averaged each of the sides. So if we look at our beaker people's results, their average was 0.82, and then we subtract that 0.82 from the answer for each trial to come up with the deviation for each trial. So 0.82 minus 0.70 is 0.12. You can see the average deviations for each trial, and then I want to just simply average those deviations to give me the average deviation. So the beaker people got 0.09. Now, if you did not do this correctly, pause the video now and redo the cylinder to get a new answer. If you did get that number correctly, let's look at the cylinder answers. So the average there was 1.03. Incidentally, when I'm dealing with sig figs, if I'm averaging numbers, essentially I'm kind of adding them together. So what I usually do is however many decimal places. Remember, when we're adding with sig figs, we're paying attention to decimal places. So however many decimal places most of my answers are, that's what I take my average to. So that's why I rounded that to 1.03. So now I take the deviation for each trial, and you can see there's our deviations for each trial, and so there is my average deviation. So as we might expect, since the cylinder was marked more precisely, we got a more consistent answer. We got a lower average deviation with those guys. And so the cylinder people had a better precision for this experiment. Okay, so take a minute now. Again, pause the video again on your sheet. Just summarize this statement. What does the average deviation tell us about the data collected in an experiment? And when you're ready, hit play again. Okay, now another term that we look at besides precision is a term called accuracy. And this is probably what you think it means. Accuracy is how correct your answer is. In other words, it's how close your answer is to the accepted answer. Okay, so if it's right or not. Now, there may or may not be an accepted answer. In science, sometimes you're doing something where nobody knows for sure. But this would be the answer scientists say, most scientists are getting, or what the book answer is. This is your accuracy. Now, this just is try to illustrate the difference between accuracy and precision. If we look at target A, you can see they have good both. We're hitting the target, we're hitting the bullseye, and we have a very close grouping. So the precision refers to how close your grouping is together. So you can see in answer C, our precision's not very good. We're all over the place, nor is our accuracy very good. We're not hitting the target very well. But in B, you can see we have very good precision. The grouping is very close together, but the accuracy is not so hot because we missed the target. Again, usually, if I like a good precision, okay, this person is probably a good shooter to get that grouping. Maybe their gun was just calibrated wrong. The sighting was to get that. So good precision does not mean good accuracy, but again, it's a good sign. So this is the difference between the two terms. So accuracy, again, is how close you are to the accepted answer. Like I said, there's some situations where you might not be able to describe it if there is no accepted answer. Now, just like we have average deviation, which put a number on our precision, we can calculate and put a number on the accuracy by calculating what's called percent error. Now, here's the formula for how we calculate percent error. Again, notice we're interested in the absolute value. So this is your experimental answer minus the accepted divided by the accepted. So these are the same numbers that are going to go in here. Again, it's the absolute value. And then to make it a percent, we multiply it by 100. So let's look at an example. Let's say we've done this experiment trying to figure out the formula mass for water. Periodic table gives us the 18.015. Here's our 3 trial results. So again, we need to know what the experimental answer is, so we're going to average the 3 trials. So we get 17.7 as the average, which is our experimental answer. We're going to pop that into our formula for percent error. There's our formula. The experimental is going to go in. The accepted is the 18.015. We'll just do some simple calculations there. It gets a little iffy with sig figs because this is mixed. When I subtract the 17.7, 18.015, I rounded it to 0.3 because I only had 1 decimal place I'm subtracting. So I took my 0.3, which only had 1 sig fig, divided by the 18.015. That's why I took my answer to just 1 sig fig. You can make a case for other things. It gets a little hairy with these ones. But there we go for that one. Okay, so now back to our examples. If we're looking at the density of water, here's our beaker people and cylinder people's results again. Now we could look up in books that the accepted value is at 25 degrees Celsius is 0.997 grams per milliliter. So what I'd like you to do again is to pause the video now and calculate the percent error for each side. What was the percent error for the beaker people and what was the percent error for the cylinder people? And then play this when you're ready. Okay, so now that you have your answers for the percent error, we want to answer which group had the best accuracy. Remember, that's measured. Now bring these answers to class. We will talk about these answers that you got in class tomorrow. So just to summarize, we want to just answer, what does the percent error tell you about your data? Go ahead and write a summary statement for that. Now, if you've been instructed to, after you're done, you want to search and do part 2 of this video, which is going to deal with something called the Q test.